Welcome to this third video of a playlist about the preparation of phenols. You can find a PDF version of the slides under the Community tab of my channel. In this video I'll show you some examples of electrophilic aromatic substitutions, including direct oxidative substitution of hydrogen by a hydroxy group and the oxidation of aryl silanes, boranes and metalated arenes. The direct hydroxylation of benzene would be great for the industrial manufacture of phenol, but despite some promising laboratory results, no process has yet been found that economically beats the Hock process. Electrophilic hydroxylations can be conducted under acidic conditions with electrophilic hydroxylating reagents, for instance hydrogen peroxide. A cationic intermediate is formed, and such reactions work particularly well with electron-rich arenes. Arenes may also be metalated, either directly or by halogen-metal exchange. Treatment with an electrophilic alkoxylating reagent can then yield a protected phenol. Benzylic heteroatoms can facilitate the direct metallation of arenes with transition metals by chelate formation. Oxidation would then yield a phenol or a protected phenol with high orthoselectivity. Because late transition metals are often difficult to oxidize, catalytic amounts of metal may be sufficient to attain a complete conversion. A huge number of examples of such reactions have been and are still being reported. Unfortunately, the scope of such hydroxylations is of course limited to chelate-forming starting materials, and in most examples the chelate-forming group cannot be removed from the product. Let's check some specific examples. This here is a direct hydroxylation of benzene with hydrogen peroxide, catalyzed by iron 3. Because phenol is much easier to oxidize than benzene, 44% yield of clean phenol is not too bad. A still higher yield could be attained in the hydroxylation of tetralene with a cyclic diacyl peroxide. Apart from the acidic solvent, no further catalyst was required. The regioselectivity was low, but no benzylic hydroxylation occurred. Another interesting alternative is the nitrate-mediated acetoxylation shown here. Again, the reaction mixture was slightly acidic. I'm not sure how this works, but it may involve the addition of acetoxy radicals to cumene. Interestingly, no nitration of Riedel-Crafts acetylation occurred. Actually, while nitrating electron-rich arenes, acetylated phenols sometimes result, as in this example. Instead of the expected nitroxylenes, mostly an acetoxic xylene was obtained. A plausible mechanism is the addition of acetate to the carbocationic intermediate, followed by elimination of nitrous acid. This mechanism does not, however, explain the formation of 4-acetoxycumene in the previous example. The direct electrophilic hydroxylation of substituted arenes is of little synthetic value because of the low regioselectivity and yield. In these examples, an excess of arene was oxidized with one equivalent of concentrated hydrogen peroxide and aluminum chloride. Electron-rich arenes like toluene or anisole gave the best results, mostly ortho and para-substituted phenols, along with some chlorinated products. Nitrobenzene did not react at all. This here is one of those many examples where a chelate-forming arene is oxidized with catalytic palladium acetate and a stoichiometric oxidant, diacetoxyiodomenzene in this case. The conditions were relatively mild and the target product was obtained in fair yield. A still better yield was attained in this example. Again, an aryl acetic acid was heated with catalytic palladium acetate. A piperidinone ligand resistant to hydrogen peroxide was also added. Despite deactivation by the nitro group, hydroxylation of the chelate complex proceeded smoothly, and the target phenol was obtained in 70% yield. Here a remarkable rearrangement occurred involving a C-C bond cleavage. Treating the starting aryl propionic acid with bis-trifluoroacetoxyiodomenzene and a Lewis acid yielded mainly an acyloxyarene, but a maybe unexpected isomer. This result again shows how important it is to carefully characterize each product. Spectra of the product shown here and the isomer with the methyl group pointing down will be almost identical, and both products can only be distinguished by X-ray crystallography or by advanced NMR experiments. Examples have been reported of the direct hydroxylation of protected or unprotected anilines. Here, N-allyl aniline was heated with a slight excess of benzoyl peroxide and sodium acetate, and both a clean ortho-hydroxylation of the phenyl group and a benzoylation of the amino group occurred. N-phenylphthalimide can be hydroxylated with a mixture of oxone and trifluoroacetic anhydride. Again, ortho-hydroxylation was the main outcome, despite the steric bulk of the phthalimido group. In this example, 5% of palladium acetate was added as catalyst and the oxidant was peracetic acid. An ortho-hydroxylated anilide resulted as the main product. One important over-the-counter analgesic is 4-acetamidophenol, also called paracetamol, the acetanilide of 4-aminophenol. In view of the previous examples, paracetamol cannot be prepared by direct hydroxylation of acetanilide. Fortunately, N-phenylhydroxylamine rearranges cleanly to 4-aminophenol, as shown here, in the so-called Bamberger rearrangement. The hydroxylamine can be prepared by careful reduction of nitrobenzene. Today, most paracetamol is produced by this route. Also, phenols can be hydroxylated directly, again in the ortho position. Here, iodoxybenzoic acid was the oxidant and an excellent yield of a substituted catechol was obtained after only 1 hour at 0 degrees Celsius. The protected aminoethyl group remained unchanged. This is an ortho-hydroxylation of a protected phenol by intermediate formation of a ruthenium chelate. No oxidation of the isopropyl group occurred. With anisole, however, no chelate was formed, and mainly position 4 was hydroxylated. Even protected thiophenols can be hydroxylated at the arene without oxidation of the sulfur atom. The procedure shown here was based on an intermediate aryl borane, then oxidized to the phenol with an excess of sodium perborate. Here, 2-nitrobenzaldehyde was hydroxylated by palladium chelate formation. The benzaldehyde itself did not form any chelate, but an intermediate imine with chloroantenilic acid did. The oxidant was N-fluorocolidinium triflate. Similarly, oximes of aryl ketones can be hydroxylated by oxone and catalytic palladium acetate. In electrophilic aromatic substitutions, fluorine is strongly para-directing, and accordingly the hydroxylation proceeded here with high regioselectivity para to the fluorine atom. In this example, a benzophenone imine was hydroxylated with 1 equivalent of copper-1 and an excess of hydrogen peroxide. No heating was required and the reaction was complete after only half an hour. Even benzoates can be hydroxylated to salicylates by intermediate chelate formation, in this case with a ruthenium catalyst. I'll show you now some examples of the ipsohydroxylation of aryl silanes, boranes, and other mononucleophilic intermediates. Here a disilane was selectively monohydroxylated with a slight excess of bis-trifluoroacetoxy-iodobenzene and 5% of palladium acetate in hot acetic acid. Again, substitution occurred para to the fluorine atom. No chelate was formed here, and the acetoxylation presumably proceeded by insertion of palladium-4 into the carbon-silicon bond. Aryl silanes can also be oxidized without any transition metal catalyst. Here, ipsohydroxylation with the aid of an excess of fluoride and hydrogen peroxide yielded the target phenol in excellent yield. In this example, a brominated naphthalene was first converted into a Grignard reagent and then into a boronic ester by treatment with trimethyl borate. Without isolation, this boronic ester was then oxidized to the naphthol with hydrogen peroxide. Aryl Grignard reagents can also be oxidized directly to protected phenols, for instance by treatment with peroxides. One potential byproduct here could have been benzophenone, but nucleophilic attack at the peroxy oxygen was faster than attack at the carbonyl group. Alternatively, polar organometallics might also react with elemental oxygen, as in this example. Intermediate peroxides will also quickly oxidize the polar organometallic. To attain high yields, it's important to dry the oxygen, for instance by passing it through a dry ice cooling trap. Let's have a look at some of the many potential side reactions. Phenols are easy to oxidize, and this is the weakest spot of this strategy. If an excess of oxidant is used, the product may be oxidized further. Here, for instance, a cresol was hydroxylated at the methylated 4 position under mild conditions. Moreover, benzylic positions, in particular those of phenols, are also readily oxidized to alcohols or ketones. Then, catechols can even be cleaved to muconic acid derivatives. In part 5 of this playlist, you can find a number of oxidative transformations of phenols that can occur as side reactions during the preparation of phenols by oxidation. Particularly insidious is the oxidative dimerization of phenols, which is sometimes difficult to detect by NMR. Here are some further examples which you can also find in the description of this video. Many of these are chelate-mediated oxidations, of unfortunately limited scope and little economic and practical relevance. The next video of this playlist is about the preparation of phenols by aromatization of cyclohexanones or cyclohexenones, and by cyclocondensation and cycloaddition reactions. See you!